In a previous video, we demonstrated how to model multi-unit chilled water systems using CogenS cooling module. Now we will build on the same project and demonstrate how to model thermal indirect absorption chillers when evaluating cogeneration technology. When starting the cogeneration systems modeling section, the cooling system must be modeled first if absorption chillers were to be considered to increase the thermal production utilization of the CHP system. Evaluating the feasibility of absorption chillers depends on the relationship between the electric and heating load profiles and duration curves. In this example, the electric load is always higher than the thermal load on the duration curve, but it is not always the case on the load profile plot. To increase the CHP system efficiency, we must minimize or eliminate any CHP thermal production waste by making sure the thermal load is at least equal to the electric load. In CogenS, there are 3 different methods to do this, but before we discuss these methods, first, we need to enable the distribution of the cooling load over a system of electric and absorption chillers and define the chiller types and efficiencies. Since we have already studied the most suitable electric chiller system for our project in the conventional section, we can use the same electric chiller specifications. Choosing between single or double effect absorption chillers will depend on the cooling load size, the supply hot water or steam temperature, and the heating fluid used, meaning steam versus hot water. Since our heating system fluid is hot water, our only option is to use single-effect absorption chillers, which typically exhibit a 0.7 coefficient of performance. Now we need to size a new chilled water system with absorption chillers in consideration. The first option is to utilize the Re-Opt API service provided by NREL, which will require us to enter more system input in other sections of CogenS listed in the reminder message here. The Re-Opt API algorithm will utilize these input parameters to recommend the optimal mix of renewable energy, conventional generation, and energy storage technologies to meet cost savings, resilience, emissions reductions, and energy performance goals. Among the many outputs that the Re-Opt API provides is the annual cooling load distribution between the electric and absorption chillers. When the Re-Opt API server is finished optimizing, the peak cooling demand of both the electric and absorption chiller systems is automatically populated in the rated output fields. Here, our calculated absorption chiller system size is at 70 tons and the electric chiller system size is at 245 tons. We can apply the same design number of units and unit size for the electric chillers as we did in the conventional system, and we can use only one absorption chiller and apply a 15% sizing factor, which will bring us to 80 tons. To see how Re-Opt distributed the cooling load, we can calculate the model from the Tables tab. We can see here that CogenS has calculated the monthly and annual absorption chiller system thermal energy consumption, cooling tower electric consumption, as well as the air-cooled electric chiller consumption. By looking at the total load profile for each chiller system type, we can get a good visual of the load distribution throughout the year. To plot the new electric and thermal loads after the cooling system model, we first calculate the domestic hot water system model, which will give us zeros since we did not include it in our project. Then we go to the Energy Profiles tab and calculate both the initial indicators and the new profiles. Finally, we can plot the new electric and heating load duration curves, then compare them with the original ones to understand how including the absorption chiller affected them. We can immediately notice how the new heating load duration curve has flattened and increased at the lower loads for more than 5,000 hours, which will help minimize waste heat, produced by the CHP at low loads. If we go to the microgrid sizing tab, we notice that the REOP algorithm has optimized our CHP system size at 423 kilowatts. This explains why the cooling load distribution for the absorption chiller was mostly at low loads to make sure that the waste thermal production of the CHP is minimal, as we see in the heating load duration curve area plot on the right. The second method for determining the cooling load distribution is purely an energy-based one. CogenS looks at the electric and heating load profiles and attempts to increase the thermal load at time steps where the electric load is higher. This method is very beneficial when the CHP system size must be higher due to certain project constraints such as available space and grid interconnection. By choosing the energy option and clicking Calculate, we see that the calculated absorption chiller system size has increased to 245 from 70 tons, and the electric chiller system has decreased to 16 from 245 tons. Since the electric chiller system size is too small, we can ignore any distribution between systems and consider only the absorption chillers to serve the entire cooling load. Since the absorption chiller efficiency part load curve shows best performance at loads higher than 50%, we should consider a one chiller system and size it at 280 tons. Now we can click Calculate and model the system. Looking at the new electric and heating loads, we notice how the new heating load has become always higher than the electric load, which will dramatically reduce the CHP waste heat. The third and final method that we can use for cooling load distribution is a user-defined one. The user will manually import a time series of cooling load factors that apply to the electric chiller system in the Excel sheet format shown. CogenS will multiply these factors time series by the total cooling load time series to determine the electric chiller's load. Then CogenS will multiply 1 minus these factors by the total cooling load time series to determine the absorption chiller's load. That concludes our discussion. If you like this video and looking for a one-on-one demo of CogenS, please reach out to us at info@jisenergy.com. Stay tuned for more videos like this on our website and YouTube channel.